the periodic table of elements. This is our modern day version of the periodic table of elements. You have this copy in your OneNote. I've given you a hard copy of it now that you can use, but we need to look at some of the history of the periodic table, how it was developed, who developed it, etc. The periodic table was developed because it was observed long ago that the elements that we find on the table tend to follow a repeating pattern, and they have very similar characteristics. When we talk about repeating patterns, one of the examples we can use is the days of the week repeat. They go from Sunday to Saturday and then repeat. Months of the year, we start with January, we end with December, and then we start over with January for the next year. We have 4 seasons generally. And if you're a musician, you know that the arrangement of the piano keys in octaves are repeating in their pattern. Those are all called periodic patterns because they repeat. The periodic table of elements, the elements themselves, when arranged in a certain fashion, will also show a repeating pattern. And when we look at them, we're going to look at the repeating pattern found in what we call columns, groups, or families. They're all interchangeable, as you'll see as we go through this lecture. The first person to actually recognize and try to arrange the elements in a pattern was a Russian scientist by the name of Dmitry Mendeleev. Mendeleev lived in the 1800s. He was able to arrange elements in both horizontal rows, and he did so by their increasing atomic weight. And he observed that when the elements were arranged in order of increasing mass, that similar properties would start to appear, and you would see a repeating pattern as the arrangement continued. So what Mendeleev developed was a periodic table that looked like this. At the time, he only saw about 72 different elements, whereas on our modern table, we have something like 119 different elements. So for example, he had the element H, which is hydrogen, and then lithium, but they didn't know about helium, which would actually fit in between. They also knew beryllium and boron and carbon, nitrogen, etc. But they didn't know about the different ones that we know today. But he did the best job that he could do. One of the things that he noticed was that beryllium and iodine tended to be out of place. Beryllium is found right here with a weight of 128, and iodine was a weight of 127. But what he noticed was that iodine behaved very similarly to these elements here called fluorine, chlorine, bromine. And as most scientists will do, they just simply decided, well, sometimes it's not perfect. He couldn't explain why iodine was where it was with a lower weight than beryllium with a higher. But again, he was using something called atomic weight, but they just left it at that. So this is what they came up with as the original periodic table of elements. And then Mendeleev is generally credited. If you had to answer like a Jeopardy question, Mendeleev would be the one who would be credited with first discovering, creating the periodic table. But in reality, our current modern day version of the periodic table was developed by an Englishman called Henry Moseley. And in 1911, he discovered that you shouldn't arrange the elements by their weight, which we call atomic mass, but it would be better to arrange them by their atomic number, which is actually the number of protons found in the atom. And he used a technique called X-ray spectrometry to actually do this. And Mendeleev didn't have this ability in his day. to actually determine the number of protons through the use of technology, but as time advanced, technology improved. Moseley generally is not given much credit here because of the fact he died very young. He wasn't very old. He was actually died very soon after his discovery, and he's just not a well-known person. What happened was he was a soldier in World War I, and he didn't survive the war. But from that, he is actually the one that's credited with the current periodic table that you now have as a handout that you should keep in your binder so that you can use later on. So the modern table, this is what we see now, where we have the elements are arranged in things called columns, and they're also arranged in things called rows that travel across. Columns, of course, go down. So one of the things we need to note is that rows are called periods, whereas these columns are going to be referred to as groups. The periodic law states that chemical and physical properties of an element repeat in a regular pattern when they are arranged in the order of their increasing atomic number. So the number of protons determines the arrangement. So what you're going to be doing based upon this lecture is you're going to be taking the blank periodic table handouts that I gave you in class, and you're going to make two color-coded periodic tables. So the first thing I'd like you to do is to label what we call the groups or the families. These are also called columns. They are going to be labeled across the top of the periodic table. And I need you to label your table this way. So on both of the sheets of paper, you're going to label the tops of the columns with these numbers. 1 all the way down to the last one, you're going to actually label it 8 and 18 in parentheses. So you can pause this and get out both of the handouts, the one that says metal on the top and the other one that says family, and go ahead and label them. And then after you've done that, I would like you to put in what we call this little stair step. And you'll see that it's right here, starts on 313, and it kind of zigzags as you see. If you want to, you can also add that arrow if it's not there, I can't remember, and you would also add that little line right here between 2 and 3 on that row. So pause and label all of that. Okay, when you come back, the next thing you're going to do is what we call the periods or rows. With the periods or rows, these are going to be the outside over here on the left, the rows. And remember, rows go across the periodic table. So label them 1 through 7 like this. So you can pause while you're doing that, undo it on both of them, and then you can stop. One of the things that you should note is that the families actually tell you the oxidation number of an element. So all of the elements in family 1 have an oxidation number of 1. All of the elements in family 2 would have 2. All of them over here in 818 actually would have 0. This is something that the table can show you, and you'll see that later when we have to do some stuff with those oxidation numbers. One of the things you're also going to have to do is you're going to have to color code these two tables. The table that is labeled metal, nonmetal, and metalloids, you're going to make a color code key. And the first key is you're going to need to note that we're going to color elements on this table that are called metals red. This looks pink on the screen, but it's actually the color red. That's your first key. And the elements that will be colored red will fall into this region here. Those are all referred to as metals. The next color you're going to use is blue. This is blue. That is going to represent the metalloids that are found on the periodic table, and you will find them here. And then the final color will be green. And green will represent elements that are referred to as nonmetals, and those will be found in this section of the periodic table here. So one of your checkpoint assignments will be to color code the metal, nonmetal, metalloid table with these three colors. So this slide right here will be a great model guide for you to work on your assignment. Some things about each of these that we need to know. Elements that are considered metals are always going to be found on that left-hand side of the periodic table. They are good electrical heat and, let me back up, they're good electrical and heat conductors. They conduct electricity and heat very well. That's why we make wire out of metals and cooking pots out of metals. They're said to be malleable. What malleable refers to is that you can pound it flat and it will flatten out without shattering. So you can actually pound them to very thin sheets. Metals are also ductile. Ductile means that you can stretch them into a long, thin wire and they won't snap. And metals are said to have luster. So luster refers to anything that will reflect light, and it tends to be silver in color. Metals are almost always, 99% of the time, solid at room temperature, with the exception of the element called mercury, which is actually liquid. It's the only liquid metal that we know of. And as a preview of things to come, all metals will have an oxidation number of either +1 through +3. So it could be +1, +2, or +3. Those are all the metals. And another thing that you need to note, which won't make much sense now until we actually start talking about compounds, but when they do form compounds, metals will lose electrons. The other major group here are the nonmetals. Nonmetals are opposite of metals. So if metals are found right on the periodic table, nonmetals will be, or excuse me, if metals are on left, nonmetals will be on right. Metals are poor conductors of heat and electricity. Metals are good. So we make insulation out of nonmetals because they don't conduct heat or electricity. If you try to pound them, they will break. They're brittle. If they're a solid, because not all nonmetals are solid. You can't pull them into thin wire, so they're not ductile or non-ductile. They do not shine. They don't have that reflective quality that metals have, so they have no metallic luster. Their state of matter varies. Some are solid, some are liquid, but most of them are gases. And it just kind of varies. You have to kind of just memorize which element is which. And their oxidation number can be anywhere from -1 to -4. And when they form compounds, they're going to gain electrons. These two bits of information are just kind of reference right now, but we'll come back and visit what an oxidation number is and what happens when elements join to form compounds when we talk about compounds in a future unit coming up. Metalloids is the third. They're the least present on the periodic table. They're the group that's found between the metal and nonmetals. They have properties of both metals and nonmetals, so they're either or, they're kind of in between. They're usually like a metal in the sense that they have that metallic appearance, though they'll have luster and be shiny. But if you were to try to pound them flat like a metal, they would be brittle like a nonmetal. They would shatter and break. They don't conduct heat and electricity very well, so they're more nonmetal in that respect. And there's only a few elements. The elements that are going to be metalloids would be boron, silicon, germanium, arsenic, antimony, and beryllium. And boron, silicon, and arsenic are elements that I had on your list. Those are the only ones that I put on your list that were metalloid. So on our next table, we're going to, that it says families at the top, you're going to record, or you're going to create another color code key, and we're going to shade it completely different. That's why you're doing two different tables. So the first table you're going to color as a metal, non-metal, metalloid, and the second table you'll color in this fashion here. So our first, and again, you should have all of the numbers for the periods and the families, which go across, periods go up and down, labeled. So that should all be done. And the key will be the following. Column number 1, we're going to color red, and they're referred to as the alkali metals. Column 2, you're going to color orange, and that will be referred to as the alkaline metals. Columns 3 through 12, which we refer to as the valley or the transition metals, will be colored blue. Column number 7, so we're switching way over to 717. This is the group that we refer to as the halogens, and they will be colored yellow. Column 8, 18, is going to be colored green, and that is referred to as the noble gas family. And then the final one will be down here in this strip that's kind of pulled out. This is referred to as the inner transition metals, or sometimes called the rare earth elements, and you're going to color that purple. So the colors you will need for the key: red is going to be the alkali metals, orange will be the alkaline metals, yellow is the halogens, noble gases are going to be green, the valley or transition elements will be blue, and you will have the inner transition metals here as purple. So each of these families, and remember a family is the column going up and down, they all have certain characteristics. Like family members tend to have similar characteristics. They behave somewhat the same. Well, the elements can be arranged in this pattern to do the same thing. So let's look at what they are. So for each of these we have some characteristics and properties that we need to look at. So the alkaline metals, these are the group that are found here in column 1 that you're coloring red. These all have what we call a +1 oxidation number. So any element that's found there on your list would have an oxidation number of +1. It's real easy. That's a common characteristic. They are all very shiny, but they're considered soft metals. Literally, you could cut them with a butter knife. And they're extremely reactive metals. When I say reactive, that I mean that if you were exposing them to air or water, you would see a violent reaction. They tend to explode. Now, the alkaline metals you don't find naturally out there in the environment. They actually, because they're so reactive, they form compounds. And to get them, we have to split the compound in half to get the metal out of it. So you don't have to worry about, say, sodium blowing up in your face because you won't find it outside. You'll generally find it in the compound called sodium chloride. So they're never found free in nature. And when we do get them, we have to manufacture them. And you, as a science student, couldn't probably find them and purchase them. The alkaline metals, this is our second column, and you're color coding that column orange. These all have an oxidation number of +2. So column 1 is +1, column 2 is +2. Nice pattern there, periodic. They're always found in a compound form. You won't find them free in nature either, and they're very reactive themselves. They're not just quite as reactive as the alkali metals. And Then we move on to the transition metals. These are this 3 through 12 section called the valley. You're coloring them blue. And their valence electrons vary. So you can't say this one's 3, this one's 4, this one's 5. Later, when I give you the oxidation numbers, you'll just have to write them down on that sheet. This is where we find what we call precious metals. When you think of metal, I think when the word metal is mentioned, this is probably what you think of, elements found here. So these would be things like gold and silver and copper, iron, nickel. Those are all common metals. They're not very reactive. You can go out in the ground and dig them up if you know where to look. You can find them in their pure metallic form. They tend to be valuable. You know, we see them as value, so we put a lot of monetary weight on them, gold especially. And they can be colored. Most metals are silver, but some of the transition elements are colored, such as gold is gold and copper is copper, and iron tends to be a reddish color when you find it in the metallic form, and cobalt is blue. So these are colored elements, and their oxidation number is going to vary. You just basically on this one have to memorize them or make sure you have them on your list so you can use it later. The next group way over here, this is column number 717. We colored it yellow. These are referred to as the halogens. The elements that fit in here are the following. That would be chlorine, fluorine, bromine, iodine, and astatine. Astatine I don't have on your list, but the others you should know their symbol. And the letters behind them refers to their state of matter. So for example, fluorine would be a gas, chlorine a gas, but iodine's a liquid, or excuse me, bromine's a liquid, iodine's a solid, astatine would also be a solid. So again, they're in the 717 group. They all have an oxidation number of -1. They're considered nonmetals. So on the first table that you color coded, they would be found in the green area versus all the other ones over in the red, over there on the left. They are also very reactive, but you can find them in their pure non-metal state, in the element state, and you find them they exist in all three states of matter. So some of them are gases, some are solids, some are liquids. There ain't all the things. Most metals, except for mercury, are always going to be in the solid state. The noble gas group here, they're in the last column, 818. We colored them green. They do not have an oxidation number. They have literally oxidation number is 0. They are very non-reactive. They don't combine with any other element to form compounds. They're kind of boring. And we also have another name for them called the inert gases. So we have noble gases and also this term called the inert gases. And you are actually breathing them as we speak. They're found in very small amounts in our air. Mostly our air is composed of nitrogen, 80%, oxygen, somewhere around 20%, but that's not really true. It's like 19.9%, and what's left are a lot of these different noble gases that you're breathing in, such as helium, and neon, and krypton, and argon. The last group on this family table you're going to color would be the intertransition metals. These are also called the rare earth elements. They're found down here in this kind of pull-out strip that you colored purple. And why it's pulled out is because it actually fits on that black line. All of these would be squished into that black line. And if you expanded the table, then it would be shooting clear off the page. So they just actually pull it out and drop it down. There are 30 elements found here. They're referred to as the lanthanoid and the actinoid series because lanthanoid is found first, and this is the first element here, actinoid is here. Just a little bit of trivia. They are almost all radioactive. Few of them are naturally occurring elements in the planet, but almost all of them are man-made elements. There are 2 of them found on your list that you will have labeled onto this periodic table. And what we've done when we say man-made is we literally force an element to become a new element, usually by hitting it with neutrons and making it take more neutrons than it normally would. Protons and electrons will follow. So what you're going to do, and we'll use both elements as, or this slide here as an example, you also need to label the elements found on your list where they fit in the periodic table. So for example, hydrogen fits here in column 1, period 1, whereas zinc is found over here in period 4, column 12, kind of like playing Battleship. You need to place all of the symbols on both tables. You don't need to fill out the whole table with all the symbols from the periodic table, just the ones that are on your list. Do it in pencil. It works better in pencil because then when you color over them in colored pencil, it doesn't tend to smear and you don't lose where the symbol is. So for the family table, it would look like this when finished. When you color it on that paper, it'll look just like this. The metal, non-metal